looking forward to our presentation. I think we've all introduced ourselves. We've got some guests here and some regular members. So with that, we'll have our program, some short announcements. There's refreshments you can grab anytime you like. With that, then I'll introduce our speaker for tonight. Evan Lewis is a fifth-year astronomy PhD student at West Virginia University. He studies pulsars and other types of radio transients, including fast radio bursts and bursts from magnetars, in order to understand their emission properties. He's also an avid science communication and spent part of his graduate career working at the West Virginia University Planetarium. So you all put your hands together and welcome Evan Lewis tonight.
Cool. Well, thank you so much. Really, thank you for having me. I love giving these kinds of public presentations. Before I get started, I just want to flip through some of my slides, make sure you can see everything okay, you can hear me, my connection isn't too awful. My internet and my computer have well. Okay, that's good. So yeah, if anything goes awry during the presentation, please just let me know. But yeah, thank you so much for the kind introduction. I think you covered all the basics. I have a bunch of slides prepared, but I don't want this to feel like a lecture or a class where you just sit here and listen to someone drone on for like 45 minutes. So please, at any point, if you have questions or comments about what I'm saying, feel free to throw them in the chat, which I can see, or just shout out and interrupt me. I want this to feel more like a conversation than a lecture. So with that, I will really quickly just outline what I want to talk about today. So of course, I'm talking about pulsars, specifically my research, but just in general, what they are, where they come from, and how cool they are. So after I describe how they are created, I'll talk a bit about the properties that make pulsars so unique, and a bit about the specific parts of their population that are interesting. I'll dive a bit into my own research with pulsars, which pertains a lot to searching for new pulsars in these big pulsar surveys. I also do something called pulsar timing, where we essentially use pulsars as extremely precise clocks. And I'll finish by talking about the specific kind of pulsars I like to study. They're called rotating radio transients, or RATs. And also just the single pulses from pulsars and their kind of individual emission on smaller scales. So lots of cool stuff. So pulsars are created at the end of a star's life. So before we talk about the end of their lives, let's talk just briefly about the beginning of their lives. So stars spend most of their lives on what we call the main sequence, where in their very core, they're fusing hydrogen into helium. And that fusion process lets off a little bit of excess energy in the form of heat and light. Now that energy is what allows the star to stay up. It is kind of the outward pressure that allows it to hold itself up against its gravitational pull, which kind of wants to make the star collapse in on itself. So that heat and light escapes, and of course that's how we have life on Earth, but eventually that hydrogen fuel in its core is going to run out. All of it will have been burned into helium. And what you'll see is that you'll have a helium core in the center and a shell around it of hydrogen burning into helium. With heavier stars, what we can see is this process duplicated over and over with heavier and heavier elements, until in the absolute heaviest stars, you may see something like this picture on the right. As you go deeper and deeper towards the core of the star, you'll have heavier and heavier elements fusing, until in the heaviest stars, you'll have a core of iron. Now, the thing with iron is, unlike all these elements before it, where you get a little bit of energy out from the fusion reaction, to fuse iron into anything heavier, you have to put energy in. So these fusion reactions can't really naturally take place in the cores of these stars, and so they'll just kind of accumulate these iron cores at their centers. So what happens at the very end of a star's life will depend on its mass at the beginning of its life. So our sun is, in the grand scheme of things, a pretty average to on the smaller side of a star. So our stellar lifetime will look something like the very top row, where right now we're right here on the main sequence, burning hydrogen into helium. Eventually, it will collect a helium core in its center, and maybe in our sun, maybe in some bigger stars, we'll get one step past that and get a core of carbon or oxygen. But after that, it will just kind of slowly fizzle out, and we'll be left with a white dwarf, which are just kind of inert, dim, cooling stars, not doing much. But in the heavier stars, where we get this core of iron accumulating in the center, what will happen is you're getting more and more of this gravitational pressure pulling the star inward as if it wants to collapse. Usually the fusion process will help it stop collapsing, but you have this inert core of iron in the center, which isn't creating that outward pressure to counterbalance it. Once that iron core kind of reaches a critical mass, what we get is a supernova explosion. These are by far the most energetic and intense events that we have witnessed in our universe. These giant, giant stars and the cores of iron in their center will collapse on themselves in the span of seconds. Now, these cores by themselves are heavier than our sun. They've got all this excess mass on top. All of that stuff is collapsing in on itself in the span of just a few seconds. And what we'll get at the very end of that process will kind of, again, depend on how massive that star was to begin with. So the very heaviest stars are so heavy that all of that matter will get compressed instantly into a black hole. But what we're interested in is kind of this middle ground where there is some quantum mechanical effect that will stop the star from completely collapsing into a single point, but instead we'll have this neutron star. So a lot of the material will get pushed out, and we're left with this extremely small, dense core of neutrons. And the reason we're so interested is that pulsars are a type of neutron star. So I might use pulsar and neutron star kind of interchangeably throughout here. Just remember that a pulsar is a neutron star, so they're the same. Now, we've known about supernovae for a long time. This is one of the more famous supernova remnants. It's called the Crab Nebula. This is in false color, but we still have this really beautiful expanse of all of this material that was once part of a star that has now been kind of pushed outwards by this shock wave. In fact, in kind of the early days of astronomy, astronomers were able to look at the nebula and see that it was expanding outwards a little bit and kind of work backwards to estimate when it may have gone supernova in the first place. Looking back through these old records of astronomers throughout the globe, they found that this supernova that they estimated was at around the same time and the exact same position in the sky as some Chinese astronomers noted in the year 1054 that a guest star had appeared in the sky. So to them, they obviously didn't have high quality telescopes. So to them, it just appeared like a blurry yellow star that had just kind of appeared at some point. And with the advantage of nearly 1,000 years of science since then, we now know that this nebula created a pulsar. It just so happened to be a star which formed a neutron star. And we call it the Crab Pulsar because it's in the Crab Nebula. And it's one of the most studied pulsars and really objects out there because we've known about it for so long. So these are some optical images of it on the very right. And it's an extremely energetic and fast rotating pulsar. It rotates around 30 times per second. So it's really cool, and supernovae are just amazing in general. So what are neutron stars like? I mentioned that they are very heavy and very dense. Now, the average mass of a neutron star is about 1.5 times the mass of our sun. Anything lighter than that would be able to kind of hold itself up. But once you get to about 1.4 solar masses, that's when gravity will kind of win that war and the star will collapse inward. So these neutron stars are about 1.5 times the mass of our sun, but they're only about 10 kilometers across. So, or maybe 20 for the diameter. So this mass, heavier than our sun, could fit reasonably above New York City. So these are extremely, extremely dense objects. Sometimes I'll ask a poll question. I didn't set up a poll, so if you feel so inclined to shout out an answer or put something in the chat, I've put the densities of some really heavy, dense metals on the left here. And I want you to just imagine to yourself, how dense do you think a neutron star is when compared to things like this?
Anybody in the room?
Yeah. I'm gonna say the last one.
Yeah, I would say that.
Well, you're all
I think we all like E.
Yeah, I think I should have maybe made the answers a little more spaced out, because the answer is way, way more than 1,000 pounds per square inch. It's on the order of trillions of pounds per square inch. In fact, if you took just 1 teaspoon of a pulsar, it would weigh as much as Mount Everest. So these are extreme objects. And because of this process of stellar collapse, these neutron stars have a lot of unique properties. And one of them is the conservation of angular momentum. So we know that before and after one of these collisions, the angular momentum, which is just the radius times its velocity, will be the same. And in this collapse, the radius of a star to a neutron star, it will drop by a factor of maybe 100,000 to 1 million. So our sun rotates about once a month, and pulsars typically rotate on the order of once every second to a fraction of a second. Millisecond pulsars are kind of a special case, but they're the fastest spinning pulsars, and they can rotate hundreds of times per second. The same principle applies for the magnetic field of these stars. So the average magnetic field of the sun, again, depending on where you look, measured in Teslas, is, maybe a fraction of 1 Tesla. And the strongest magnetic field that humans have ever been able to create is around 42 Teslas in this giant, sophisticated laboratory in China on the left here. Again, you can think to yourselves for a second on what the average pulsar magnetic field is, but I'll spoil it for you. It's on the order of millions to hundreds of millions of Teslas. So these are extremely magnetized objects, which is the reason that we're able to study them so well, is that's what helps create their emission. And also, just as a fun fact, I got a lot of these numbers from this Wikipedia article that just lists like characteristic magnetic field strengths for different things. And one of the entries on there was the strength used to levitate a frog. There was apparently some like genuinely peer-reviewed, published scientific research where they set up a strong magnetic field, and the water molecules in and around the frog like flipped so that the frog would levitate. So I may have picked the wrong field. That sounds like a lot of fun, but I guess astronomy is kind of fun. So I'll take it. So to kind of sum up everything I've said thus far, pulsars are heavier than the mass of our sun, but they're compressed into the size roughly of a city. They rotate many times per second, and they've got magnetic fields millions of times stronger than anything we've been able to create on Earth. So hopefully it's clear that these are incredible physical laboratories that can help us study regimes of physics that we just could never recreate on Earth, at least anytime soon. So in addition to all of the cool astronomy we're able to do, there's also a lot of really interesting fundamental physics and plasma physics that we're able to glean just by learning about pulsars. Now, a lot of you, I remember seeing in some of your emails that you were watching some movies about pulsars. So you may know a lot of this stuff already, but as you know, when we look up in the sky, a lot of the stars that we see, everything that we see, is emitting light in the optical wavelengths, which is just a very, very narrow window inside the entire electromagnetic spectrum. Pulsars don't radiate visible light, at least just your kind of run-of-the-mill isolated pulsar. So we can't really study them just by using standard telescopes. We didn't know about pulsars in the 17 or 1800s. So how do we know? The answer is there are a bunch of ways, but they were first discovered using radio waves. So I'm a radio astronomer. I study pulsars primarily through their radio emission. I use big radio telescopes. And when I say radio, a lot of the people in my life imagine like their literal car radio, and they're trying to figure out how stars are sending us signals just like a car radio does. So to kind of use that as an example, the way that radios actually work is you have a radio transmitter. These are your big radio towers. And of course, they're not actually transmitting sound, but they're transmitting the radio broadcast in the form of radio waves. So that's actually just light that, of course, we can't see, that is being picked up by your receiver, in this case, your car antenna, which converts that incoming radio radiation into electrical currents. And then you've got some very smart computer in your car, which knows how to translate those currents into sound based on how that data is encoded. Now, pulsars aren't sending us encoded messages that they have constructed, but they are sending us radio waves, which are a form of light. So in much the same way, we have our pulsar as a radio transmitter, and they're very far away, so we have to use much more sensitive radio receivers. This is the Green Bank Telescope in West Virginia, and essentially how all these big radio telescopes work are like giant rain dishes. So the incoming radio waves will fall on this giant dish, and the dishes are constructed in a way so that they'll focus all of those radio waves to this. You may or may not be able to see it. There's a tiny dish at the very top end of this arm here. That's actually the secondary reflector. So they're first reflected by the giant dish, focused even more by the secondary dish, and then you may be able to see this box a little bit below the secondary dish. That's the actual receiver, inside of which we have all of the, it's more sophisticated than a car antenna, but essentially your car antenna is up there taking in the radio waves and converting them into digital signals and saving them. Now, in terms of how we knew pulsars were around, we know that they're rotating, and we know that they have these two beams of radio waves, but the rotation axis and the magnetic axis, where the radio waves emit from, are not aligned, which means that as this pulsar rotates, we see this very stable periodic flash of emission as the pulsar's beam kind of rotates past our line of sight. They're extremely stable rotators, as we'll see, but this periodic emission is how they were kind of first discovered as a unique, interesting astrophysical object. So whenever I give a talk about pulsars, I like to tell the story of how the first one was discovered by Jocelyn Bell Burnell. So in the 1960s, she was a graduate student at Cambridge in the UK, and her job was to build this radio telescope behind her, which does not look like a standard radio telescope we'd see today. It's actually just an array of these antennas. So all along here, you have these dipoles, which do the same thing. You know, they will translate the radio waves into currents, but they just look a little different. Now, her job was to look for something completely different. She was looking at objects called quasars, which are, you know, formed by the supermassive black holes at the centers of other galaxies, which create these really powerful jets. So as she's building this telescope and analyzing the initial data from it, she's supposed to be looking for quasars, but as she's looking over the data, she sees something interesting. And this is the actual data of the first detection of a pulsar. Back then, they were actually using these kind of pen recorders like you'd see in a movie on a lie detector or a seismograph or something like that. So it's easy to see in the bottom image here, but you can see this kind of regular periodic string of pulses. They were spaced about a second and a third apart, So her advisor is like, oh, this is too perfect. It's probably just man-made interference of some kind. But as she continued to track it, she noticed that it was consistent with a sky position and not a location on Earth. So there's a difference between the solar day, which is 24 hours, and the sidereal day, which, because of the Earth's revolution around the sun, a star that's in one place on the sky will reach that same place 4 minutes earlier the next day. So she was able to notice over the course of a few weeks, hey, this is consistent with an astrophysical object. Originally, it was called LGM1 for Little Green Men because there's this incredible regularity to the pulses. Its period didn't seem to change over the course of weeks. And so it's kind of convincing that how could something natural possibly be so regular? But they only had one, and for a while, there wasn't much you could do with only one of these objects. And then eventually, Jocelyn was able to find another one coming from a completely different part of the sky with a completely different period. And this kind of cemented that they were these astrophysical objects. And just a few years after some astronomers had proposed for the first time that neutron stars could possibly even exist as the endpoint of a supernova, the first pulsar was discovered and published. Now, the story doesn't have the best ending. This was the 1960s, and maybe women weren't treated quite the same. So the discovery of pulsars won the Nobel Prize for her advisor and the head of her group, but not for Jocelyn, who did the work and the analysis. Now, she has been extremely gracious. To this day, I've been able to see her talk. She still gives these regular talks at all these different conferences, and she's been extremely gracious. She just says that she's happy that pulsars and astronomy in general were rated highly enough to even consider giving a Nobel Prize at all. But since then, she's kind of become a hero in the astronomy community at large. She's received essentially every other science award under the sun. So despite not getting the Nobel Prize, in the end, she really has been recognized for her work in kickstarting this whole field of pulsar astronomy. So that was 1967, when the very first pulsar was discovered. If we flash forward today to 2023, there are over 3,000 pulsars that have been published. There may be even more that may not have been written up and peer-reviewed and published in scientific journals, but there are over 3,000 pulsars that we know of in our galaxy, which is incredible. And the way that we're able to find a lot of these pulsars is through pulsar surveys. So the animation that's showing up right now, this is in the galactic coordinate system. So the very center of this globe corresponds with the center of our galaxy. And overlaid are different pulsar surveys. This isn't close to all of them, but it shows the different regions of the galaxy that these different pulsar surveys have scanned looking for pulsars. And you can see that some of them will focus maybe a bit specifically on the galactic plane. Other surveys will scan the entire region of the sky that telescope can see, which is why a lot of those surveys you'll see have kind of this weird curve. One of the surveys that I work with a lot is the Arecibo Drift Scan Survey at 327 megahertz. So the Arecibo telescope, of course, was this extremely famous, world-renowned radio observatory until its very, very tragic collapse just a few years ago. But before that, it was revolutionizing the field of astronomy as well as atmospheric sciences and radar, and it did a lot. But what's really cool is, this telescope was in Puerto Rico. There were a lot of times that even when they weren't doing maintenance, there may have been tropical storms coming, and they had to lock the telescope in a specific position. So that means that they couldn't point it at specific regions of the sky. However, some very smart astronomers said, hey, the telescope's still usable, we just can't point it. But as the Earth rotates, that rotation is going to kind of naturally move the beam across the sky. So what if we set up this drift scan survey that while the telescope can't be pointed, we'll just kind of passively collect data, and over time we'll be able to use all of this previously unused time and search that for new pulsars, which I think is kind of ingenious. So again, unfortunately, Arecibo isn't being used, but we have many, many radio telescopes all over the world which are consistently undergoing these pulsar surveys. Now, of course, once you've taken all of that data, you then have to analyze it. And something that a lot of people don't realize is a big part of astronomy nowadays is just data science, is just learning how to work with giant data sets. Pulsar data is huge. Again, if you'd like to shout out an answer or throw something in the chat, please feel free to take a guess on how big you may think a 10-minute pulsar observation is. But I'll warn you, it's pretty big.
Okay. Who in the room's got a guess?
F. I'm gonna guess D.
Would you say, Eric?
I'm gonna guess about a gig a minute for 10 gigs. So D. My guess.
For D,
I like that
huh?
someone said F.
Yeah.
That was good. So I may have tricked you. It is actually D. So someone, I couldn't hear who, but someone got it right, which is awesome.
Our IT expert. Yeah.
Now, there we go. So to kind of illustrate why that is for people who haven't worked with pulsar data before, this is kind of a short cutout of some pulsar data. So in a lot of these observations, we're taking data over a large bandwidth. Here we're looking from maybe about 1200, a little over megahertz, up to 15 megahertz. And we kind of split that bandwidth into channels. I think there are 16 here, but those are kind of averaged over. For a standard search observation, you might get something in the range of 512, 1024, maybe even more channels. So hundreds to thousands of channels. And they also have extremely short sampling times. So you can see that, all of these different vertical lines, those correspond to individual samples, and this is only 100 milliseconds long. So a normal sampling rate may be something like one data point every 100 microseconds-ish. And so if you kind of do the math, you're taking close to maybe 1 million individual data points every single second. So that will very, very quickly balloon up just for one observation. And surveys, with radio waves, we're only really able to point a very small beam on the sky at a time. One of the other surveys I work with at Green Bank, its beam size is roughly half the angular size of the moon. So imagine taking something that big and you want to scan every pointing for a couple minutes, maybe 5-10 minutes. It takes hundreds of thousands of beams to scan the entire sky. So you get to the end of a pulsar survey and you've got maybe hundreds of terabytes to analyze. Now, this analysis is complicated even further by the way that we have to process the data in order to look meaningfully for pulsar signals. Usually we look for periodic signals, but one of the ways that this is hampered is by something called dispersion. So I'll wait for this video to load. So pulsars are broadband emitters. If you tune your radio station to, let's say, 94.3, that radio station is broadcasting in a very, very, very narrow range of frequencies around 94.3 megahertz. But here, we know that pulsars emit all over the radio spectrum. So its emission here, this is the emission from one pulsar pulse, is kind of modeled as 3 different waves. This is just the high frequency part of the wave, the middle frequency, and the low frequency part of the wave. And what you'll see here is the emission is running into this dense cloud of gas. Again, this is just an illustration. But in the interstellar medium, we know that there is some charged matter. It doesn't even have to be a lot. But any ionized material will cause a radio wave to be dispersed. And what that looks like is the low frequency part of the wave will be delayed more than the high frequency part of the wave. So if we're looking at an individual pulsar pulse, this is something that it might look like. we have the high frequencies up here. You can see that they're arriving earlier than the low frequencies, and there's this kind of characteristic sweep. Now, how strong the delay is and how curved this line is depends on how much stuff there is in between us. So if we're searching for new pulsars, we don't know how much stuff there is in a particular direction, because we're looking, even at one pointing in the sky, it could be at any depth in our galaxy, right?
Evan,
So,
can I ask a question?
yeah, of course.
I hate to interrupt, but when you're saying that the longer wavelengths get slowed from the shorter ones, you're actually talking about an index of refraction because of interstellar medium.
That's exactly right. Yeah. So the formula has something to do with the density of free electrons, because it has to do with I don't know if it might be similar to the index of refraction. I'm sure the derivation is somewhere in there, but yeah, that's essentially what's happening, is the signals being dispersed by that charged material, and so it's just delayed as it moves through.
Thanks. Sorry for the interruption.
No need to apologize. So what we have to do if we're going to be processing this data and we don't know how dispersed a given signal may be because we're searching for new objects, we kind of have to correct for this dispersion at any and all dispersion measures, which is our term for how curved this is or how strong the delay is. Now, of course, that's difficult. It is very computationally expensive, but something that's really cool is using the degree to which this is curved, we can work backwards, and if we have an independent distance measurement to a specific pulsar, we can estimate how much material there is between us and that object and use that as an analog for distance. So as a part of this process to kind of be able to estimate the distances to a pulsar, the astronomy community has developed these very in-depth electron density maps of the galaxy. So to the left is kind of a local one. The red X is our sun. I believe this is something like a parsec. And on the right is our entire galaxy. But I just think it's, really amazing that something that hinders our ability to discover pulsars, this dispersion that we have to account for, is actually something that we can turn around and use it as a tool to learn about the electron density at different points in our galaxy, to learn about the interstellar medium, and even if we're studying extragalactic objects, the intergalactic medium. I just think it's amazing that we're able to take this thing that is usually a problem for us and turn it into a scientific tool. So that's why science is amazing. So I've talked a bit about how we search for pulsars, and I want to talk a bit about how we study them in more depth. So this is kind of our really simple toy model of how pulsar emission works. Again, it's got this really strong magnetic field, and it's emitting radio emission at these two beams along its magnetic axis. So we know that pulsars are emitting this light over long periods of time, and we also know that light is a form of energy. We also know that pulsars are powered by their rotation. Their rotational energy is what allows them to create this radio emission, but it acts like a battery, right? They're not being powered by anything externally, it's just that rotation. So because it's giving off light, that energy is leaving the system. And over time, that means it's losing rotational energy, and it's going to spin down over time. This is a really, really, really minor effect. If you look at a standard pulsar with a standard rate of spin down, its rotation will get longer. So one rotation will take about 30 nanoseconds longer over the course of 1 year. So this is an extremely, extremely subtle difference. But using this, we're actually able to characterize a lot about a pulsar just from measuring its period and its rate of spin down. So what I'm showing here on the right is something called a PP dot diagram, or a period derivative diagram. So each of these individual points here is a pulsar. Its position on the horizontal axis represents its spin period, all the way from 1 millisecond here to about 10 seconds. And its position on the vertical axis represents its spin down rate. There's also a lot of very busy lines happening in the background, basically from a very basic theory about how pulsars emit energy, making a lot of assumptions. We can estimate a lot of physical properties about pulsars just by measuring their period and their spin down rate. So here, these lines represent lines of constant age. We can kind of guess how long ago this pulsar was formed. We can guesstimate their surface magnetic field. So that's the downward sloping lines with the G at the end for Gauss. And we can also estimate their spin down luminosity, or how much energy they're giving off in the form of light, or what rate they're giving it off by. And just by looking at this plot, it's very busy and it's probably hard to pick out a lot, but we can see that there are definitive separate populations within the pulsar community. So here, kind of in the middle of the plot, we have canonical pulsars, just your standard run-of-the-mill pulsar. They've got spin periods of a little less than a second, and their spin down rates are kind of right in the middle. But we've also got this separate population here. It's clear they're a little bit different. These are called millisecond pulsars. So not only do they have much lower spin periods, they spin much faster, their spin down rates are lower, so they're even more consistent clocks. Their period changes even more slowly. And it's clear there's something going on here, right? These are clearly different objects. They have different stories. And you may be able to see that a lot of them have circles around them, which on this plot represents that they're in a binary system. So what are millisecond pulsars and why are they so different? We have been extremely lucky, and we've been able to study, I want to say, hundreds of millisecond pulsars throughout our galaxy. And essentially what we see is something like this. Pulsars can be in binaries with other systems. In this case, in a very large companion star, it may be on the main sequence, it may have left the main sequence, but it hasn't gone supernova yet. And the pulsar is so dense and heavy that its gravitational pull pulls in a lot of material from the star. So all of that excess gas kind of gets stripped off of the companion and begins to orbit the pulsar. This is what we call an accretion disk. So these accretion disks will surround the neutron star, and they will continue to rotate, and the gravitational pull of the neutron star, its high mass, will cause this mass to accelerate. So all this stuff around the neutron star is spiraling in, and it will eventually land on the neutron star. When it does this, it will kind of transfer its angular momentum onto the neutron star as it lands. So this process will actually spin the pulsar up. So you will go from a pulsar which had a spin period of maybe a second to something that has been spun up by the material from its companion so that it's rotating really quickly. And as you can imagine, millisecond pulsars are extremely interesting, and they're an extremely active field of research, because not only can we look at the pulsar and its radio waves, but we can look at its companion in optical wavelengths if it's a star that's still going through fusion. And the accretion disk itself is superheated due to kind of dynamical friction. So we can also look at high energy emission that's coming off of the accretion disk. So we can look at it in X-rays. This is an X-ray satellite up here, and in gamma rays. This is a gamma ray satellite down here. So millisecond pulsars can teach us not only about pulsars, but about stellar evolution, about kind of gravity and these dynamics of accretion. They're really incredible. And my focus is not millisecond pulsars. So I know enough about them, but I'm far from focusing specifically on them. But suffice it to say that I could give a whole talk just on millisecond pulsars and their dynamics. You may also see that these two circles don't envelop everything. And I've circled the third group kind of in the top right corner, and these are magnetars. So again, it's clear that they're pretty separate from the bulk of the pulsar population. So it's pretty clear that something different physically must be happening here. In this case, magnetars, again, are neutron stars. They're just like pulsars in that regard, but we believe that they are powered not by their rotation, but by their extremely strong magnetic fields. So as you can see, they're at the very far right of the diagram, which means they have the slowest spin periods. I think the slowest spinning neutron stars have had periods on the orders of tens to hundreds of seconds. So it's hard to power their energy through their emission through rotation that way, but we believe that their magnetic fields are so strong that they're able to give off energy in that way. And magnetars, again, are really unique and worthy of a whole talk in and of themselves. We can study some of them through radio waves. We can study a lot of them, again, through X-rays. And they are some of the most highly magnetized objects in the known universe. So neutron stars in general display a wide range of variety, and pulsars just take up a small group of them. So I've talked a bit about the different types of pulsars, but how do we know all this stuff, right? How do we even measure the spin down rate? How do we learn about their companion and the dynamics of these binaries? And the answer is through a process called pulsar timing. It's very precise, but it's very mathematically kind of in depth. So I'll give the SparkNotes version. What we do is we build a model of the pulsar's rotation and astrometry over time. So essentially, we can pretty quickly say, okay, I can see the pulsar has this spin period, and we can start from there. But over long periods of time, we may notice a difference between our very simple model of the pulsar's rotation and what we actually observe. So in a specific pulsar's case, we'll undergo what we call a timing campaign, where we'll get data on it pretty regularly spaced, maybe every week or 2 weeks for a year, ideally more. And we'll build up our model and refine it over and over and over so that it matches the data as closely as possible. And we do that by measuring something called a residual, which is just the error between our model and reality. And it's just an error in time. This is when we thought the pulse would arrive. This is when the pulse actually arrived. This is just an example of what a residual plot will look like. So essentially what we do, we take all of these residuals that we have measured, all of these errors between our model and reality, and we'll plot them over time. In the top left is an example of what a well-timed pulsar will look like. We are accounting for all of the pulsar's rotational properties, its motion throughout the sky, its location on the sky as accurately as we can. And all of these points are centered around a residual of 0. There's some noise because we'll never be able to perfectly time every single pulse, but you can see that our errors are on the order of fractions of a millisecond. So we're doing a pretty good job. Whereas if we have one of the parameters wrong, it will show up as a very characteristic pattern in our residuals. So for example, in the bottom left, if we've gotten the rate of spin down wrong, over time, our residuals, our errors will get larger and larger in a kind of exponential curve. If we get the position on the sky wrong, it'll look like the top right, where we have this kind of periodic variation in the errors as the Earth moves around the sun, etc. And we don't do this by hand or by eye. Of course, we have these incredibly sophisticated algorithms which will take in all these residuals and kind of search all of the different parameters to try to find the solution that fits these residuals the best. And what we get at the very end is a timing solution, which again is just a list of the parameters that we have measured using these observations. This is an example screenshot of what one of these timing solutions will look like in a published paper. And of course, I'm not going to go through all of it. You may not be able to see all of it, but especially in the bottom 2 sections, each of these rows is a measured parameter. And you may be able to see that at the very end of each of these numbers is a number in parentheses. And that's an error on the very last digit. So to give an example, again, if you can see it, in the middle of the second section, this is the spin frequency. So this is the how many rotations per second. And over a period of, let's see, about 2,000 days, we've been able to constrain its period to an error of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimals. So we know its rotation rate to that extreme accuracy. And that is what is so powerful about pulsar timing, is its ability to measure all of these different aspects of a pulsar, especially if they're in binaries. We can also measure all of the binary parameters. So how long does it take to make an orbit? How far separated are the two objects? How eccentric is the orbit? Is it really circular, or is it more of a weird ellipse? And just by taking all of these observations and using our knowledge of what these parameters will do to the residuals if they're wrong, we can learn all of this, which is incredible. And pulsar timing, because it allows us to measure all of these aspects of a pulsar, allows us to make new discoveries. So for example, some things that have been discovered with pulsar timing, the first ever planet outside of our solar system, the first planet that we ever confirmed to be a real planet not orbiting our sun, was a planet orbiting a pulsar. And we were able to find it because of the planet's effect as it orbited around the pulsar, its effect on our timing residuals. In the middle, pulsars were able to help us confirm Einstein's theory of general relativity, or at least confirm a prediction of it, which is gravitational radiation. So in this case, it was a binary system. We timed this pulsar, this is over 30 years here, and general relativity predicts that as these two objects orbit each other, they will let off just a little bit of gravitational radiation because they're so massive. And in terms of a binary system, that means that the orbit will kind of in-spiral. Very, very subtly, but it will, which, means that they're moving towards each other and the orbit is getting a little smaller and a little faster. So pulsar astronomers measured the shift in the time it takes to complete one orbit over 30 years. And it may be hard to see any deviations, but the black points are the measurements and the line behind it is the prediction by general relativity. If I remember correctly, the two agreed to like over 99.5% accuracy. So this is really incredible accuracy. And without getting too much into it, there is a whole field of pulsar science known as pulsar timing arrays, where we're trying to do something kind of similar. Basically, if you've heard of LIGO, you know that they are trying to, or they have detected gravitational waves by having these two arms. And as a gravitational wave will pass through the arms, one of the arms will get stretched and the other will get kind of squished. And that will cause their apparatus to shift in a way where they can measure the strength of the gravitational wave passing through. Our goal in these pulsar timing arrays is to do something similar on a gravitational scale, where our arms are the distance between Earth and all of these pulsars. So we're essentially collecting dozens of pulsars scattered throughout the galaxy, which are extremely, extremely precise rotators, which means we can account for all the excess types of noise that we may see in their residuals. And the idea is we're looking for different gravitational waves than LIGO will look for. But if a gravitational wave passes through these arms, we'll be able to detect that signature in the residuals. And because we have so many pulsars, we know how those shifts should be correlated. So it could one day help us detect direct gravitational waves, which would be pretty amazing. I'm going to finish off here by talking a bit more about the specifics of one area of my research, which are rats and the single pulses from pulsars. So pulsars are extremely far away, and they're very weak emitters. If you stood on the moon with a cell phone, that would be brighter than any astronomical object emitting that we can detect in radio waves. So in order to be able to detect these objects, we have to find a way to strengthen their emission, or at least strengthen our ability to detect them. And the way we do that is by looking for periodic signals in our data, because we know that pulsars are periodic, and kind of stacking data chunks of that length on top of each other to get a clearer signal. So you can kind of see that process on the left here. This is something we call folding. An individual pulse from a lot of pulsars may not be specifically extremely bright, but by adding up hundreds or even thousands of them, they will add up much faster than this kind of random noise will, and we'll get a kind of pulsar's fingerprint or a pulse profile. Now, these are really stable over long periods of time, but on the right here, this is showing some zooms in on some individual pulses from a specific pulsar over just 22 seconds. And you can see that over that short period of time, there's a great amount of variability in their shape. So studying pulsars in the long term can be very rewarding for a lot of reasons, but by studying the individual pulses from pulsars, we can learn a lot too about their emission physics. And one of the ways that this kind of ties in is with RATs, or rotating radio transients. So again, on the left here, this is maybe a standard pulsar observation. On the vertical axis is time, so the span of the observation runs up the plot, and on the horizontal axis is the phase, or the point in rotation. What these vertical lines are telling you is that we're seeing very bright, consistent emission at the same point in a pulsar's rotation, which again, we know we're looking at periodic objects. We can see that it's emitting at the same point in its rotation. Great. But you can see that for a standard pulsar, they're pretty consistent. This is over the course of 10,000 seconds, so we can't zoom in too much, but you can see that we're getting this bright emission the whole time. On the other hand, this is what an observation of a rat may look like. They're extremely sporadic. They've got bunched pulses, and then you may see nothing for minutes, hours. They may turn off entirely. In the most extreme cases, you might only see a few pulses and then never see anything again. Now, all of our evidence says that rats are pulsars. We know that they're neutron stars. We know that they're rotating. We can find periods for some of them, but clearly there's something different. So there are many theories about why. One of them is that rats are running up against what we call the pulsar death line. So if I go back to that period derivative diagram, you can see that in this orange shaded area, there are very, very few pulsars in that region. Now, that has to do with our theories of how pulsars create emission. Basically, we think that past that point, there just isn't enough rotational energy to power the emission. Our theories aren't perfect. It has to do with a lot of plasma physics, which is why there are some pulsars on the other side of that line. But some theories for why rats are that way is that they're approaching the end of their ability to create emission. Some other theories are that rats are creating giant pulses. So we know that other pulsars create these giant pulses, which are thousands of times stronger than their average pulse. We've seen them in normal pulsars, and so one theory about rats is maybe they are pulsars which are just really intrinsically weak, so they create giant pulses, but those pulses are the only ones that are detectable to us. They just look like normal pulses because they're so weak, and the kind of standard emission is just too dim for us to see. Some more exotic theories, one of the ones I like is that rats are just regular pulsars which have an asteroid belt or a bit of debris orbiting around them, which may just be obscuring the radio emission. This is less favored. It definitely doesn't explain all the rats we see, but I just think it's pretty cool. And to finish up, because I've talked for a while and I really want to get to all of your questions, to talk a bit about the kind of work I do. Grad student life, I'm working on like 5 or 6 different projects at once. Some of the ones that I think are really cool I'm working on the long-term timing of a few pulsars that were discovered with the Green Bank telescope, and they kind of fall right on the edge of being rats and being normal pulsars. So sometimes they show pretty consistent, reliable emission. We can look at them the normal way, but sometimes on other days, they're really sporadic and we'll only see some pulses. So what I'm doing is doing that process of pulsar timing using two methods. One using the kind of regular pulsar method, and one just by getting the times of arrival of individual single pulses and comparing them. So I want to see if for pulsars that kind of fall in this intermediate region, is one method of studying them better than another? Maybe for specific, values of their burst rate or different things like that. How can we learn more about them? I'm also studying some really cool data from a magnetar. Now, there are very few magnetars that also emit radio emission in the same way that a pulsar does. A lot of magnetars don't produce that kind of periodic pulsed emission, but they will produce X-ray emission and other stuff like that. We got some really cool radio data from one of the very few pulsar magnetars that acts like a pulsar. And so I'm studying that. I'm also looking at their single pulses to see, is there some overlap between the characteristics of single pulses between magnetars, between pulsars, between rats? Is there anything different we can learn? And most recently, working with the Arecibo 327 megahertz survey, I worked on the discovery and timing follow-up of a few of these cool millisecond pulsars that are in binaries. So in addition to doing my usual radio astronomy, I got to work with some optical data, some X-ray data, some gamma ray data. I got to do a little bit of everything, which is one really cool part of studying millisecond pulsars. And to close things out, I always like including this in my pulsar presentations. This is a really, really famous album cover, Unknown Pleasures by Joy Division, and it is actually an image from a pulsar paper. So this is from the 1970 PhD thesis of someone called Harold Kraft. And what he was doing is he was at the Arecibo Observatory. He was looking at the individual pulses of some of the first pulsars ever discovered. And what this plot is, I've put the caption at the bottom if you can see it. It's 80 successive rotations of actually the first pulsar that was ever discovered, the one that was discovered by Jocelyn Bell Burnell. And what he did was to demonstrate the variability from pulse to pulse is you just take the shape of its emission and stack them up. And you can see in this really unique shape all of the different kinds of pulse shapes that you can see, even in 80 successive rotations. So one of the coolest album covers just so happens to be a pulsar plot, which I like bragging about. And that takes me to the end of all the slides I have. So thank you so much, and I would love to have all of your questions fired away at me.
We've got some questions here and probably online as well. So Jeff, will you man the handheld microphone, and anybody that has a question or, yeah, go ahead.
I got a lot of questions. I'll probably tear you apart with some of them. The first question I have is on the slide where you show the derivative of the x-axis is the time and the y-axis is the rate of change.
Mm-hmm.
Yeah, thank you. Okay, there you go. Yeah, so in between the green and red circle, I see some companion stars. I'm assuming that over time, when the material from those companion stars go into the neutron star and adds to their angular momentum, they're going to move over to the left, aren't they?
That's right. So it's a bit of, we're looking at different stages in that process. So we've seen some pulsars that are in the very beginning stages of accretion. There may not be emitting radio waves, but we can still see that they're in a binary with another star and accretion is starting to happen. So they maybe haven't spun up to these very fast periods yet. You'll also see some spread here just because the rotation period the pulsar can get to depends on what kind of star it's in a binary with and the evolutionary history of that star. So, for example, some of the pulsars in the middle here might be disrupted recycled pulsars. So what happens is we know that pulsars are created in supernovae. So at some point, these were just two regular stars orbiting each other. Neither of them had gone supernova yet. Usually we'll see pulsars in binaries with higher mass star, because if you have a binary with a lower mass star, well, once the pulsar goes supernova, it'll just get blown away. What may happen is if you have kind of this standard, let me go forward a little bit, or backwards. So if you have this kind of standard binary with a pulsar and a companion, this companion can still go supernova. So some of our explanations are, okay, well, halfway through the accretion process where it started to spin up, this star suddenly went supernova, or something else happened. There was some, energetic event that caused accretion to stop. And so this pulsar is kind of half spun up, but hasn't gotten all the way spun.
Okay, thanks. The on the album cover graph that you showed, every period was different. So does that mean that the surfaces of these, or the magnetic fields of these neutron stars, are changing in dynamic?
Yeah, so there's actually part of the reason I really love studying the single pulses from pulsars is by studying them, we can learn about kind of the magnetic field surrounding the pulsar. So the way that we understand pulsar emission is that it's created above the surface of the pulsar. There's this kind of atmosphere of charged plasma around it. And through the rotation and the strong magnetic fields, will kind of create this beam of radio waves. The kind of standard model is like a cone, right? But depending on what is happening inside the neutron star, depending on what is happening inside that cone or inside the atmosphere surrounding the pulsar, we may, the emission may just, the beam of emission may change shape, or the way that it sweeps past our line of sight may wobble back and forth a little bit. They're very dynamic atmospheres. So in some pulsars, kind of long term, we've been able to predict that there may be changes inside the star. They're called starquakes. It's really cool. It doesn't sound like a real scientific term, but we think the stuff inside a neutron star can go through one of these quakes, which will cause the pulsar's rotation to kind of have a glitch. That's over longer periods, but even over these really short terms, from rotation to rotation, we can see a lot of variability, probably because of the really dynamic environment in the magnetosphere, in the atmosphere surrounding the pulsar, but also because this radio beam is kind of created by individual pairs of particles which are accelerating and letting off radio waves. So from rotation to rotation, you've got a whole new population of particles, essentially. So that's why on these short time scales, it will be kind of fuzzy, because we're just seeing these different patches of emission throughout this region.
Thanks. I got one more, and then I'll shut up and let somebody else have a shot here. on Jocelyn Burrell's telescope, it looks like just wires out in a field. I'm going to show my stupidity. I don't know anything about radio telescopes. How do you aim that thing?
Ooh, that is a good question. And I haven't worked enough with telescopes like that to be able to give you a good answer. I know that we essentially think of those. It's essentially just an array of a bunch of individual antennae. And even today, we have interferometers. We have arrays of radio telescopes, which are, stationed. Some of them are all in, one region. Some of them are throughout multiple countries. And these interferometers what you can do is you can either have them each create these kind of individual beams all next to each other, or kind of focus on one specific location. So I believe, again, this was a really rudimentary telescope, so they didn't really have the same focusing capacity. I believe with things like that, they'd be more sensitive to regions on the entire sky, but perhaps maybe looking at just the output from one of the antennae, you'd be able to hone in on a more specific region. Again, that's a kind of guesstimate because I don't work with telescopes that look like that. I don't think anyone does anymore. So I'm just not remembering.
It might have been more like Arecibo, where you just were waiting for the sky to pass over it.
But yeah, but original Arecibo, they could move the thing up.
Yeah.
But that one in the field is just a string of wires. How do you aim it?
Yeah.
I'll let somebody else ask the questions now. I can hawk myself.
Okay, other questions?
I have one. I'm Eric. When you were talking about the rats, I wanted to make sure I understood. Are these pulsars that are not as regular as your normal set of pulsars, and these are more erratic and sporadic in their pulsing? Did I understand that correctly?
That's right, or at least that's what we see. So, like, we don't think that their rotation rate is changing. We don't think that they are actually like turning their emission on and off. We just know that on our end, what we're detecting is what looks like really sporadic emission. So in order to explain it, we have to say, okay, either its intrinsic emission is just really weak, or its emission is kind of turning on and off. Again, we have these individual particle pairs that are accelerated, and that's what creates the radio emission. So in some systems, it's possible that that process gets disrupted, or that it, if a pulsar is at the end of its battery life, if it has almost no rotational energy left, it may not be able to consistently create that emission. So it's still rotating at the same rate, it's still at the same place in the sky, but we think that its ability to create that radio emission either turns on and off, or is so weak that we can only see the strongest part of it. And we see something in normal pulsars called nulling, which is a bit more on longer time scales. Like, it'll emit really consistently for a while, then completely shut off, then turn back on and be consistent for a while. Here with rats, it's more like you'll see a pulse and then a minute, and then you'll see another pulse, and then maybe 5 minutes later, you'll see a few pulses in a row. So they are pulsars that we just think their emission is more sporadic. It turns on and off at what seems like random intervals.
So do you think some of them could possibly be explained by precession of the neutron star, where the precession is changing our position in relation to being able to observe the pulse? Is that a possibility, or is the rotation period still so quick that can't be a factor?
That's a really good question. And as far as I know, we're able to observe precession, but it happens on much slower timescales. The one example I can think of is in a binary system, so that may have an impact on it. But I know that in the case of this one pulsar that I'm thinking of, it was visible for a set of years, and then its rotation axis kind of very slowly precessed outside of our line of sight. And for like 15 years, we didn't detect any emission from it because none of it was passing through our line of sight. And it has either recently come back into our line of sight or will in the next couple years. So as far as I know, I think that precession happens on longer timescales.
Okay, that makes sense.
Especially because we think that rats tend to have slightly longer pulse periods. We think they tend to be slightly older, which means that they're probably changing on longer timescales. So they're probably not really quickly precessing They probably haven't recently been in some kind of dynamic interaction that's causing them to wobble really quickly. As far as I know, our best guess is, excuse me, its inclination like that isn't changing too rapidly.
Okay. I have another question if you guys don't mind. You had mentioned where like the very first extra solar planet was discovered using pulsars. After I would expect after a supernova that you wouldn't have planets in that system anymore. So do you think that in order to find a planet around a pulsar means that that planet must have been formed after the original supernova?
So you cut out a bit. I think you asked, you would expect that a supernova would always have a planet, or eventually there would always be planets in that region?
No, so I would expect a supernova to destroy any extrasolar planets. So
right.
Would you think that this planet then formed from the material after the supernova?
Yeah, so I'm thinking about this particular system, and I know in some cases there are these binaries, and the pulsar and the other star are so close together. Pulsars produce this energetic wind of particles. It's called a pulsar wind, that actually blows out from the pulsar. And in some systems, we can see the companion star kind of getting torn apart. In addition to this kind of accretion that we see from those, main sequence stars that can create millisecond pulsars. So depending on the evolutionary dynamics, and this is a field of active research, is how this evolution might happen or what might happen at the end of a binary's life, it's possible that in some cases, a companion star has been blown away so much by this energetic pulsar wind, or so much of its material has been, torn off into this accretion disk, that what's left has such a low mass that it looks like a planet. To the best of my knowledge, in the case of the first extrasolar planet, I don't think we've been able to see it in optical wavelengths, but from the characteristics of the binary, we can estimate its mass, but that doesn't tell us much about what it's made of. So one possibility is that, in the accretion disk around the pulsar, depending on the circumstances, I would imagine it's not impossible for some clumps to form. We can even see in the binaries we have now, there are some clumps of gas that over a long period of time, sure, they could probably create planets, but it's also possible that that planet is just the husk of what's left from a star. It might not be made of rock or, what we're used to seeing from a typical planet, but it might, we might expect to see that there's a little bit of a core left over from that star, and that might be what's orbiting this pulsar.
I see. Okay. My last question, I'm sorry. I didn't really get the gist of what the defining characteristic difference is between magnetars and pulsars. Is a magnetar just basically again a neutron star that isn't pulsating? Is that what's happening?
Yeah, so the major difference is where they get their source of energy from. So if I go back a little bit to that diagram, did they show up here? Did I go too far? Here. There we go. So so we've got some magnetars in like the top right corner here. The main difference is where they get their emission power from, what powers their radiation that we see. For pulsars, they're rotation powered, and that's true for regular pulsars and for millisecond pulsars, is their rotation is what creates their emission. in the case of magnetars, their rotation is so slow that the luminosity of their emission is brighter than the total amount of rotational energy they have. So it is impossible for magnetars to be powered by their rotation because there's just not enough rotational energy there for them to create it. Instead, we know that they have extremely strong magnetic fields, and the decay of their magnetic fields can create radio emission and can also create this high energy emission. And their magnetic fields are so strong that they can account for the luminosities we see from these magnetars. So pulsars are powered by their emission. Magnetars tend to rotate slower and are powered by their magnetic fields.
So they could or could not be what had once been more rapidly rotating pulsars that then slowed down and became magnetars. Is that a possibility?
That is a possibility, and the fact that we see a kind of middle ground here, it's a very active field of research. There's not a definitive answer, but that's very likely. That we know that especially in the beginning of a star's life, when it's first born, maybe it was rotating slower, but it had a stronger magnetic field. Maybe some pulsars, when they're first created or early in their lifetime, are magnetars. We know that magnetars tend to, you can see that they're at the top of this graph, which means that their period is changing really rapidly. That's indicative of really young stars, where pulsars tend to be older. So especially the fact that we've seen submagnetars have these outbursts typical of younger neutron stars, and then also maybe later have this pulsed radio emission typical of pulsars. It's a pretty leading theory that these magnetars will eventually become pulsars. Not all of them, but we think there's a pretty good evolutionary pathway there.
Okay. All right, I'll let somebody else ask a question if they want to.
Okay. Any other questions? I've got one, so be thinking of yours. Evan, great presentation. What we know about Cepheid variables and their use in distance measurements because of their consistent output of luminosity. I'm thinking that pulsars, could they be used as distance measurements as well with their consistent rotation and pulsing?
So, and it's been a while since I've learned about Cepheid variables, so I forget how that relationship came to be, but I believe it has something to do with their magnitude, like their optical magnitude. So I think because we can relate the period of their variation to their intrinsic luminosity, and from that estimate their distance. Unfortunately, that relationship doesn't exist for pulsars. Their rotation rate has nothing to do with how far away they are. However, the fact that they are so stable can be used to kind of triangulate us. In fact, and I might try to pull up an image here if my laptop cooperates. If you remember seeing images of the Voyager probe and the golden record that went on the Voyager probe, there was a bit that took up the majority of that record. And it basically looked like a point with all of these lines radiating away from it. And these lines were kind of notched. They had different, sets of lines going through them. That was actually a pulsar map. That was a map of the 10 near, I believe it's the 10 or 15 closest pulsars to our solar system, and those notches represented their rotation period. And because, again, they change their rotation rates so slowly, we have faith that if some other civilization is out there and finds that, the rotation rates of these pulsars are going to be the same, and we will be able to kind of triangulate where we are and where our sun is based on those 10 pulsars and our distances to all of them. So it's slightly different. We can't really use them for distances to Earth, but we're still able to do some really cool stuff with them. And for those 10 closest pulsars, I'm sorry.
No, go ahead.
I was just going to say, for those pulsars, I know we kind of indicated some distance to them. And I'm not sure exactly how we estimated the distance. Probably just a best guess. It was probably pretty rough. But because they're so consistent, we can use them to kind of navigate.
Very good. Thank you. And then you had mentioned that there were over 3,000 pulsars identified in our galaxy. Is there any estimate of the number outside of our galaxy or in the universe?
That's a good question. We haven't discovered any pulsars that are definitively outside of our galaxy, that are in other galaxies. But from the amount of pulsars that are in our galaxy, and we can use that to estimate the birth rate of neutron stars, we have a pretty good handle on the rate of supernovae in most galaxies. We can probably estimate that in other galaxies, especially ones like the Milky Way, spiral galaxies, there are probably a similar density of pulsars. There's no reason to believe that anything totally extraordinary is happening in the Milky Way that causes pulsars to be here and nowhere else. They're just too far away in other galaxies to detect them. Because pulsars form from supernovae, they are probably more prevalent in older galaxies where stars have had the chance to go through their life cycles, and also, places where you don't have active star formation, but you have kind of an older population, is probably you would find a higher density of pulsars. But again, we expect them to be in most galaxies. Anywhere that you have supernovae, you can have pulsars.
Very good, Evan. Thank you. Any other questions here? Jeff, go ahead.
I got a couple more. Just keep saying stuff that makes me.
It's only 11 o'clock in West Virginia. So.
I'm a night owl. That's okay.
You're talking about the gold plate on Voyager and a little map of quasars, but wouldn't that mean that they'd have to be on the line of sight of the beam in order to have identified those quasars?
That's right. We know that there is some inclination between like the spin axis and the magnetic axis of the pulsar. I could probably go back and find that little, so we know that there's some angle between the spin axis and the rotation axis. And as of right now, we only really look for pulsars, at least their radio emission, from Earth. So we know that there are definitely pulsars out there that we on Earth can't detect because we're just unlucky and the radio beams of these pulsars just aren't pointing at Earth. I guess the assumption with the Voyager plate is if there was another civilization that was able to find that plate and pick it up, they would probably have sophisticated enough technology that they could, they would probably have some way of moving throughout the galaxy, or at least not observing these things from one fixed vantage point, that they would probably be able to detect these pulsars, even if, again, let's say the civilization has a home planet, even if that home planet was not favorably in line of sight of some of those pulsars on the gold record, you probably have to assume, or at least I guess the assumption was, that those civilizations would be able to detect the pulsars somehow, is my best guess.
I got a weird one here. When you see a pulsar out there, is there any way to tell if it's been doing that for 3 billion years or for 9 billion years? Is there any way to tell how long it's been playing its game?
There are ways to get rough estimates. So again, you can even see on here these lines that have kind of the less steep upward slope. That's something called the characteristic age. And it's a very, very rough estimate, but in astronomy, that's kind of the best we can do. Based on the fact that, we expect that when these pulsars are first born in supernovae, they're spinning really quickly. We kind of assume that their spin periods at birth are extremely fast, but once we measure their spin period and the rate of their spin down, we can kind of extrapolate backwards to get a rough estimate of how long they've been around. So again, the oldest pulsars, have characteristic ages on the order of gigayears, that's billions of years, to hundreds of billions of years. Of course, these are rough guesses, so if a pulsar's characteristic age is older than the age of the universe, that doesn't mean too much physically, but it can give us a kind of order of magnitude on how young or old they are. Beyond that, especially if the pulsar is isolated, there's not much we can do.
Did you ever ask your original question before the meeting ever started?
I've been hogging the game. I can live without it.
Okay.
Such an absolutely amazing field of research, Evan. I think you're going to have a great career ahead of you as a research scientist on pulsars and magnetars and such. So I get another round of applause for Evan. Thank you very much. And keep us in touch. Keep in touch with us for your research. We'd love to know how that progresses.
Absolutely, yeah. And I really appreciate you inviting me. I love giving these talks. I love talking about how cool pulsars are. So I really appreciate it. I had a great time.
Thank you very, very much, Evan. Okay, so let's transition over to our announcements for the evening. Just a few announcements, I think, that we want to share with you. A little look ahead of what the club has coming up.
Give me a moment to share
Okay.
Zoom here.
Hello, Doug. Thanks for joining us. I'm glad to see the virus didn't infect your computer.
Doug, can you see the slides okay?
That be your way.
Yeah, we got it. Hi, Dougie.
Okay, so hey, before we do the announcements, I've got to brag on my fellow member Jason Key's astro image that he took at Peddler Hill last month at the high altitude star party of the fireworks galaxy and the companion star cluster right in the northern constellation between Cephus and Cygnus. He was aimed up there all night and collected all this data. I think he had like 3 or 4 hours of imaging. Then he quickly scrambled back home to Manteca or Modesto and processed the image. And like by 10 a.m. on Sunday morning, this was on in our email. Yeah. I mean, have you seen the fireworks galaxy? I mean, the color and the definition, just amazing.
About 4 years ago.
Oh, is that right?
Yeah. You can also see the bright star between the cluster of the galaxy. Just below it, you can see some high nebula there.
Uh-huh.
That's a pretty deep exposure.
Yeah, it was a great clear night, and then his expertise. In fact, I'm hoping to get him to do one at the December show and tell, a little walkthrough of how he's doing his astro imaging. So, okay, this Saturday there's a amateur telescope makers gathering at Jeff's shop. Anybody needs the directions, contact Jeff. I think we all know where it's at. Later that evening, we have our low altitude star party, and we're going to either be going to the new location at Campo Seco, and Eric's going to talk about that in just a moment. So there's that where I think several of us are going to go. And then anybody that still wants to go to Highway 4, certainly that's still available too. So we might actually be in 2 groups. And the Perseids are peaking at 1 a.m. if we can stay up that late. Hopefully get a good meteor shower. So.
That's about the time moon's gonna be popping.
Is that right?
I can't remember what time moonrise is, but it's a third part of moon, so we'll be looking at one or one.
One or the other. Okay.
2:30. Okay.
And then the following weekend, on the 19th, there's astronomy in the park out at Oak Grove Park. So we need scopes and volunteers there. And it happens a couple of times a year, but it's also the schedule for our high altitude star party. So don't stay home. Whatever you do, go to one place or the other, because you'll have a good time either way. And then September 10th, our program, I'm really pleased to have Rebecca Lewis speaking to us about her PhD research on galactic centers. So
Is Evan Lewis and Rebecca Lewis related?
we don't know that yet. So okay, so Eric, those are my announcements, unless anybody has anything else that you want to bring up. And I think Eric's going to show us the map to this new location he's been scouting out for low altitude.
So here's Stockton here. You can really take a few different routes east. You can take 26 here. You can take 88, or you can also take 12. 88 actually becomes 12, but you want to head east toward Valley Springs, up in this area here. And in Valley Springs, what you want to do is take Laurel Street here.
I think that's the one and only stoplight.
Yeah,
in
yeah,
Valley Springs.
yeah. 12 and 26 all come together right here, right out Laurel Street. First right is Daphne Street. Take that, it actually becomes Paloma Road. It will then fork into, take the left fork to Watertown Road, and just a little bit more up here, we will come to Campo Seco Road. And this is the spot here, this huge pad where it's at the head of a horse trail. So this is a pretty big area for trailers with the horses to park at and plot along the trail here. But we're not interested in the trail, obviously. We just want to set up our scopes here. There's a few trees right here that I would like to cut down, but they are basically southwest. But I think if we set up along the back fence here, you can pretty much look over these trees. Other than that, it's a really flat area. It's going to be a great place, I think, to observe the meteorites. Yeah.
And is that pavement, or I think it's gravel? Isn't it?
It's small gravel. Yeah.
Okay, it's not asphalt.
It's not asphalt, it's gravel. Definitely bring, if you are interested in going there, bring bug spray. Last time I was there, I think I got bit within like 30 seconds. So bring some bug spray.
And there was a meteor that landed right next to that location. Yeah. And then zoom back out, Eric, because I think everybody can appreciate the location. That I'm hoping that we're going to get away from that dome of light that we have from Stockton, Manteca, Modesto, by going kind of northeast from that. So
we used to set up on that blue dot up there. That was Bill Cook's spot right there.
Oh,
That was Bill Cook's spot.
Oh, why'd you guys stop going there?
Because there's too many direct mercury vapor lights that can be seen from that site, and it was very disruptive.
Oh.
I don't
So-
know about this new site.
The new site, there isn't that many lights around from houses or anything. It's a pretty barren location. The only issue is let me zoom right back in. On the site here, you got this road here where people are traveling. I don't know where is that, 200 or 300 feet away. So you might see a car drive by here once in a while. But I think if we strategically park our cars in like a row here, we could probably block out a good portion of light coming from that road. I would not really expect too many people to be traveling up this road. Up this way.
On Bill's site, there were 3 mercury vapor lights that were maybe 4 miles per east. And then you can see all the lights on the houses along the lake. So this here may be completely protected from all of those.
Yeah.
I don't know.
I think when I was there probably about a month and a half ago. I think there might be one light over here. It's called the Wilderness House Trail because there's a house sitting right here. And that's like the only one. So there might be a light coming from that house. But other than that, there really shouldn't be any lights other than the eventual car going by. So.
Okay, so that's our announcements and upcoming events for pretty much August and September. We've got program for October. Jeff's going to talk to us about the annular lunar eclipse,
And you're forward.
solar eclipse. And then November, Eric has a program for us on the upcoming 2024 eclipse and some solar observing, right?
Yes, it's not. I'm not giving it. We have
A host, right?
special
I guess,
host
a speaker.
from Pennsylvania.
Yeah. And then December, you all know what we do in December. We do show and tell. So I'm reminding you and encouraging you now to think about something that you want to give a short presentation to the club on, anything that interests you related to astronomy. And the bounds are pretty wide on that. So anything, a book, an experience you had, a piece of gear you bought, anything, love to hear about you, what you'd like to present. So that's pretty much, I wanted to ask you, is anything going on with the Tri-Valley Astronomical Society that you want to share with us, or?
Yeah, well, on next Friday's meeting, we have kind of a special guest, the director of the Vatican Observatory, be speaking at our meeting. And we just want to get the word around to some of the other clubs around here. We do have it on Zoom as well. And we're thinking we may have a pretty good sized turnout. So we're looking at ways of potentially increasing the number of attendees on Zoom. So that Unitarian Church. Yeah, so our in-person meeting is at the Unitarian Church on North Vasco Road in Millwood.
I received an invite via email and okay to pass it out to all the other members. Okay. Yeah, I'll do that.
Like I said, we're still working on increasing our capacity. So if you could get together as a group and share a connection, that might help. So.
Oh, okay. Okay.
It might not be necessary.
Okay. I didn't know the Vatican had a astronomy program.
Oh,
Oh, okay. I got a lot to learn then, huh?
Yeah.
Okay.
And we are doing a Perseid meteor viewing as well at Del Park in Livermore, and we've got plans to watch the solar eclipse in October from Los Angeles College. Livermore.
Oh, nice.
And a couple other star parties at Del Park.
Mhm.
You have invited to travel to the cinema?
Oh, yeah. I don't think we're gonna do anything local in April, because probably anybody who wants to do something local will be traveling.
Yeah.
Yeah. Most of us have decided on where to go. I'm still trying to figure it out. and probably Dallas.
It's getting late. The motels are $1,000 a night now.
Yeah.
Yeah, well, Dallas is big enough that there's still lots of flights available and fairly reasonable hotels, so. So,
The Motel 6 in Kerrville wants 2-night minimum, 800 a night.
really,
I'm actually thinking of just renting like a camper and just drive to Texas.
Some of us were talking about buying a lot in Kerrville. Using it and then selling the lot.
You get a lot of money.
Yeah. Okay, well, I kind of coming to a close here. Any other comments or business?
Just one, you
Mhm.
mentioning successive months here. Don't forget to show up in November for our elections for next year's board.
Elections in November,
We
right?
actually have to have a quorum with that. don't we?
Yeah. That's correct.
And we're actively looking for new volunteers to twist their arm. So, okay, well, if that's all, then I'll thank you, Eric, for hosting us in
You're
the
welcome.
AV department this evening. Very well done.
Yeah, again, the sound was really good tonight.
Yeah. Yeah.
Pretty good.
Help yourselves to some refreshments before you leave. And I want to thank you all for joining online and in person. So we'll conclude there.